These are the answers to the AP Chemistry topics 1.1 to 1.3 MCQ Practice packet. So MCQ, multiple choice questions. You should see in the video description area a link to the packet that accompanies this video. All right, let's take a look at our first multiple choice question. Number 1, which of the following contains the greatest mass of oxygen? So we have 4 choices. Each choice has the same mass, so we have 1.00 grams, and the correct answer is going to be the compound that has the greatest percentage by mass of oxygen. So how do we calculate the percentage of oxygen by mass in a compound? Well, in general, the percentage of an element by mass is going to equal the total mass of that particular element, as found in the chemical formula, divided by the formula mass, or the molar mass, and then times 100. In all 4 of these choices, there's exactly 1 atom of oxygen, so therefore, since the atomic mass of oxygen is 16, the math involved in calculating the percent oxygen by mass would be 16 divided by the formula mass of the compound. On the periodic table, we can find the atomic mass of the elements, and for the purpose of this particular question, let's just round off the atomic mass to the nearest whole number. So sodium is 23, magnesium is 24, potassium is 39, calcium is 40. So the formula mass of sodium oxide, Na2O, would be 23 times 2 plus 16. The formula mass of magnesium oxide, MgO, would be 24 plus 16. And then for potassium oxide, K2O, 39 times 2 plus 16. And for calcium oxide, CaO, 40 plus 16. I haven't calculated the total, but let's think about this. Which of these 4 compounds has the greatest percentage by mass of oxygen? Since we're doing this math of 16 divided by the formula mass, whichever compound has the smallest formula mass will be the correct answer. So looking at these 4 choices, 24 plus 16, or the mass of MgO, that's going to be the smallest formula mass in this set, so that makes choice B the correct answer to this question. It's going to have the greatest percentage of oxygen by mass, and therefore will contain the greatest mass of oxygen. All right, this is question 2. We are given a diagram, which is a mass spectrum of element X. So we don't know what this element is. And it says, based on the spectrum, which of the following can be concluded about element X? So when you look at a mass spectrum, what information is given? This is a pure sample of an unknown element. We know that along the x-axis, we can see the mass numbers of the various isotopes. And along the y-axis, we can see the relative abundance of each isotope. So we can use a mass spectrum to calculate or estimate the average atomic mass of an element, and then possibly identify that element by looking on the periodic table. But there's no information that will be helpful about the oxidation state of the metal. So choice A talks about the oxidation state. That's not the correct answer. Choice B talks about electron sublevels. We don't get that kind of information about electron sublevels from a mass spectrum. So I've narrowed down the choices to either C or D, which both talk about the atomic mass of this element. If we were to try to draw some horizontal lines on this diagram, and then estimate the percent abundance or the relative abundance of each isotope, looks like the largest peak is 90, which has a percent abundance of approximately 51%. And then I went through and tried to estimate from this diagram the percent abundance of the other isotopes with mass numbers of 91, 92, 94, and 96. If we take a calculator and we actually do that math to multiply the mass number by the percent abundance, and then add up all those values, we would get approximately 91.4 based on the math that you're looking at here. So if I look at the periodic table, I see that element yttrium, atomic symbol Y, and then zirconium, atomic symbol ZR, and then niobium, atomic symbol, element symbol Nb, they have atomic masses that fall in that range of around 89 to 93. But in this particular case, if I had to guess what the identity of the element is, I would say it's probably zirconium, which has an average atomic mass of 91.2. Now, back to the choices C and D. We know that the atomic mass of this element is not going to be exactly 90, but just estimating from the diagram, the atomic mass of this element probably falls somewhere between 90 and 92, and that makes choice D the correct answer. Question 3. A 23.0 gram sample of a compound contains 12.0 grams of carbon, 3.0 grams of hydrogen, and 8.0 grams of oxygen. Which of the following is the empirical formula of the compound? Well, the subscripts in the empirical formula represent the relative number of moles of each atom in the formula, and we are given grams, but we need to convert each quantity from grams into moles. So we can estimate the molar mass of each element from the periodic table: carbon, 12 grams per mole, hydrogen, 1 gram per mole, and oxygen, 16 grams per mole. If we have 12 grams of carbon, then we have 1 mole of carbon. If we have 3 grams of hydrogen, we would have 3 moles of hydrogen. And if we have 8 grams of oxygen, 8 divided by 16 is 1/2, we would have half a mole of oxygen. So now that we have the moles of C, H, and O, we could write the subscripts. Of course, 1, 3, and 0.5, we're not going to use those in our final answer because we're looking for whole numbers. But if we multiply each of those subscripts by 2, then 1, 3, and 0.5 now become 2, 6, and 1. So the correct answer to this question, the empirical formula of the compound, must be choice C, C2H6O. Question 4. It says the elements iodine and tellurium have similar average atomic masses. And we can see this if we look on the periodic table. The atomic mass of tellurium is 127.6. The atomic mass of iodine is 126.9. So yes, they are similar. A sample that was believed to be a mixture of iodine and tellurium was run through a mass spectrometer, resulting in the data above. All of the following statements are true, but which one would be the best basis for concluding that the sample was pure tellurium? So we're looking for a statement that would indicate that this particular mass spectrum is not a mixture of tellurium and iodine, but just tellurium only, pure tellurium. Now, a mass spectrum does give us information about the mass number of each isotope along the x-axis and the percent abundance for each isotope along the y-axis. But what a mass spectrum does not talk about are things like the charge on the ions. So choice A talks about the charge on the ions. That's not going to be relevant to this diagram. And choice D talks about comparing the first ionization energy. We don't get that information from a mass spectrum. That's not helpful. So now we're down to either choice B or C. Choice B talks about the relative abundance of tellurium and iodine in the universe. And choice C talks about the fact that iodine consists of only one naturally occurring isotope that has 74 neutrons. So on the periodic table, we see that iodine has an atomic number of 53. That means that there are 53 protons in the nucleus. If iodine has an isotope with 74 neutrons, 53 plus 74 is 127. So there would be a mass number of 127 for this isotope of iodine. Well, in the diagram, we do not see a peak for mass number 127, so therefore this sample cannot contain iodine and it must be pure tellurium. So the correct answer to this question is C. We cannot compare the relative abundance of tellurium and iodine in the universe from this diagram, but we can prove that since there's no peak at 127, then there is no iodine present, and therefore, again, choice C is the correct answer. Question 5. A sample of a compound that contains only the elements carbon, hydrogen, and nitrogen is completely burned in O2 to produce 44.0 grams of carbon dioxide, 45.0 grams of water, and some nitrogen dioxide. A possible empirical formula of the compound is. So our job in this particular question is to figure out the correct answer, the empirical formula of the compound. So right now, we don't know what the compound is. I wrote down C, H, and N with question marks for the subscripts. We do know that it was burned completely in oxygen. So at that point, all of the carbon that was originally present in the compound, after it's burned, will be converted into CO2. That's one of the products. All of the hydrogen that is present in the compound is converted into H2O. And then all of the nitrogen present in the compound is converted into NO2. Focusing on the numbers that we are given in this problem, we have 44 grams of CO2 and 45 grams of H2O. Let's figure out how to go from grams to moles. We know that on the periodic table we can find the molar mass of an element, of a compound, in this case CO2. The molar mass of CO2 as determined from the periodic table is approximately 44 grams per mole. And the molar mass of H2O, again from the periodic table, we would figure out that's approximately 18 grams per mole. Now, if I have 44 grams of CO2, I have 1 mole of CO2. If I have 45 grams of water, you can pick up a calculator and do 45 divided by 18, and you see that you have 2.5 moles of water. But individually, we're looking at the elements carbon and hydrogen. There's no subscript for the carbon in the formula CO2. So if I have 1 mole of CO2, that would be 1 mole of carbon atoms. There is a subscript for the hydrogen in water. So if I have 2.5 moles of water, I actually have 5 moles of hydrogen atoms, because 2.5 times 2 is 5. And now that I know that I have 1 mole of carbon atoms for every 5 moles of hydrogen atoms, then I can look for an empirical formula that has that 1:5 ratio, and the only choice that does that is choice B. So the correct answer is choice B, because there's a 1:5 ratio of carbon to hydrogen. Question 6. M+ is an unknown metal cation with a +1 charge. A student dissolves the chloride of the unknown metal, MCl, in enough water to make 100.0 milliliters of solution. So we have a solution of MCl dissolved in water. And I'm just showing a flask with a solution, and inside that solution you can see there are ions of M+ and Cl-. The question goes on to say that the student then mixes the solution with excess silver nitrate, and again silver nitrate AgNO3, causing silver chloride, AgCl, to precipitate. So we have two solutions that are being combined, the MCl and the AgNO3. And when that happens, we get this precipitate of AgCl, and I'm showing a little solid on the bottom of that flask. So in the solution are still the ions of M+ and NO3-, and at the bottom of the flask is a solid precipitate of AgCl. It says that in the question, the student collects the precipitate by filtration, dries it, and records the data shown below. So in the data table, we have the mass of the filter paper and the mass of the filter paper plus the AgCl precipitate. Let's subtract those two numbers. So 2.23 minus 0.8, and we get 1.43 grams of the AgCl precipitate. The nice thing about that number, 1.43, is the molar mass of AgCl is 143, and we have a mass of 1.43. So that means that because we're just moving the decimal over two spaces, we have exactly 1/100th of a mole of AgCl. We have 0.01 moles of AgCl. Now take a look at this equation that we have, MCl plus AgNO3. The MCl is the unknown compound that contains chloride. AgNO3, silver nitrate. It produces MNO3, so some nitrate compound of this mysterious unknown metal cation, and then AgCl, the precipitate. This is a balanced chemical equation. And now that we know that we have 0.01 moles of the precipitate, AgCl, we can easily convert that to moles of MCl because there's a 1-to-1 mole ratio between those compounds, the reactant MCl and the product AgCl. So if we have 0.01 moles of AgCl, that must mean that we started with 0.01 moles of MCl at the beginning of this reaction. Now, back to the data table, it says the mass of the unknown chloride, MCl, is 0.74 grams, but we know that that is equivalent to 0.01 moles. And since there's 0.74 grams of this compound for every 0.01 moles, let's just multiply both sides of that equation by 100, there must be 74 grams of MCl per mole. So we now just figured out the molar mass of MCl is 74 grams per mole. We have 4 choices, and we can estimate the molar mass of each compound by looking at the periodic table: sodium 23, potassium 39, copper 64, and lithium 7, and chlorine 35. Again, I'm just estimating by rounding off the atomic masses to the nearest whole number. So for sodium chloride, that would be 23 plus 35, so approximately 58. For potassium chloride, that would be 39 plus 35. So I think that B is definitely going to be our correct answer, but we'll keep going. Copper chloride, that would be 64 plus 35, which is 99. Lithium chloride, 7 plus 35 is 42. So we're looking for a substance that has a molar mass of 74 grams per mole, and that makes B, potassium chloride, the correct answer. Question 7. Complete combustion of a sample of a hydrocarbon in excess oxygen produces equimolar quantities of carbon dioxide and water. Which of the following could be the molecular formula of the compound? So this question is similar to question 5 that I discussed earlier, although in this case we have only carbon and hydrogen. So back in question 5, I think we had carbon, hydrogen, and nitrogen. All right, this hydrocarbon is burned in excess oxygen to produce carbon dioxide and water. In other words, all of the carbon present in the compound is converted into CO2, carbon dioxide, and all of the hydrogen present in the compound is converted into water, H2O. The word equimolar means equal number of moles. So that must mean that this particular compound, when it's burned, produces 1 mole of carbon dioxide for every 1 mole of water. Now let's figure out about the atoms of carbon and the atoms of hydrogen so we can find the empirical formula of this compound. So if there's 1 mole of CO2, well, that would contain 1 mole of carbon atoms because there's no subscript for the carbon in CO2. And if I have 1 mole of water, there'd be 2 moles of hydrogen atoms because there is a subscript of 2 for the hydrogen in H2O. So the empirical formula of this compound must be CH2 because there is carbon and hydrogen in a 1-to-2 mole ratio. Looking at the 4 choices, the only substance that has a molecular formula that would reduce to a 1-to-2 ratio, the empirical formula CH2, that makes choice C the correct answer. There is a 1-to-2 ratio, so 4 to 8 would reduce to 1 to 2. Again, C4H8 is the correct answer because the empirical formula would be CH2. Question 8. After completing an experiment to determine gravimetrically the percentage of water in a hydrate, a student reported a value of 38%. The correct value for the percentage of water in a hydrate is 51%. Which of the following is the most likely explanation for this difference? So we have a hydrate. A hydrate is a compound that contains water as part of its chemical formula, and the hydrate is heated eventually until constant mass is achieved. So it's heated to drive off all of the water by evaporation. So after it's heated to remove all of the water, then the compound is called the anhydrate or the anhydrous salt. The difference in mass between before it was heated and after it's heated, we assume that that change in mass that occurs during the heating process represents the amount of water lost from the sample. Let's go back and take a look at the question. The student reported a value of 38%, but the correct value for the percentage of water is 51%. So the calculated value for the percentage of water by mass is too low. We have 4 choices. We have to figure out what occurred that would have caused the difference in mass between before it was heated and after it was heated to be too low. All right, I'm going to start with choice B. Choice B says that strong initial heating of the solid hydrate caused some of the sample to spatter out of the crucible. So that means that not only was water lost in the normal process of heating, but bits of solid are actually ejected from the crucible, and that would cause the change in mass to be too high. Not too low, but too high, because we're losing extra mass that we're not supposed to. So we can eliminate choice B. Let's take a look at choice D. Excessive heating caused the anhydrous salt to undergo a decomposition reaction. That means that in addition to losing water by evaporation, now this substance, this anhydrous salt, is starting to break down or decompose, possibly giving off gases into the air. That would also cause the change in mass to be too high if it's breaking down or decomposing because of excessive heating. Again, we can eliminate choice D. All right, let's take a look at choice C. The crucible had not been heated to constant mass before it was used in the experiment. Well, you might wonder, why should you heat a crucible to constant mass before this experiment? Well, suppose that there's water or moisture in this crucible. So you would heat it to constant mass because you're trying to make sure that this crucible is completely dry before you add the hydrate. So if this procedure had not been done, then there could have been extra water present in the crucible before the hydrate was even added. So now you're removing not only water from the crucible, but also water from the hydrate. That would cause the change in mass to be too high if that had not been done. So I can eliminate choice C. Now, why is the correct answer choice A? Well, let's suppose the experiment was done in a normal way and all the water had been removed during heating. But if before it was measured, before the mass was recorded, if the anhydrous salt had absorbed moisture from the air, then that change in mass before and after, that change in mass would be too low. So that's why the correct answer is choice A. All right, well, number 8 was the last question in the packet. So I hope that these answers and explanations were helpful. That's the end of the video. Thanks for watching.